Good afternoon, students. I'm Dr. Soumyajit Ghosh. So today I'm going to discuss about another aspect of isomerism of coordination complex. In the previous topic, we did discuss upon the structural isomerism of the coordination complex, but in this presentation, we'll see that what is geometrical isomerism and how many varieties of geometrical isomerism of coordination complex exist. So stereoisomerism or space isomerism, when two compounds have same ligands but its arrangement in space is different, then it is known as space isomerism. So there are two forms of stereoisomerism. One is geometrical isomerism, which can be called as cis-trans isomerism, and another is optical isomerism. The two isomers, they are mirror image to each other. So the stereoisomerism of coordination complex exists when the ligand position or ligand spatial orientation is different in the isomers. So in the geometrical isomerism or cis-trans isomerism, first we'll talk about four coordinate complex. Four coordinate complex means that there are four ligands are there surrounding the central metal atom. So there can be the two possibilities. Either it can be tetrahedral or it can be square planar. Okay. So two geometries can be possible. Tetrahedral geometry or square planar geometry where the coordination number 4. Now, in case of tetrahedral complex species, if I consider that four ligands are there surrounding the metal atom, whatever the type of ligands, whether it is similar or dissimilar, there will be no geometrical isomers. Since arrangement of every ligand or group around the central metal atom in space is equivalent. So, in case of tetrahedral complex, we will not see any form of geometrical isomerism. What will be the case for square planar complex? A planar species Ma2B2, A and B are two different ligands. It can exist in 1,2 or cis and 1,3 or trans form. No stereoisomer are possible for planar species of the type Ma4, Ma3b or Mab3 because all possible arrangements of A and B for each of these types are exactly equivalent. So the following types of complexes exhibit the geometrical isomers in the square planar complex. One, complexes containing only monodentate ligand Ma2B2 or Ma2BC or MABCD. Second, square planar complexes containing unsymmetrical bidentate chelating ligands MAB2. Number 3, square planar complexes containing symmetrical bidentate chelating ligands MAA2. Breached binuclear planar complex M2A2B4. So we'll see that each type of examples so that it will be clear. So we'll explain the square planar complex Ma2B2 where M is a central ion. Here in this case platinum 2+, oxidation state 2+, and two types of ligands are there, ammonia and chloride. So there can be two types of isomerism. One is cis and another is trans. You see that central metal ion is platinum 2+, and in the coordination sphere 2 ammonia and 2 chloride ligand is there. Now, as we talked about, the stereoisomerism deals with the spatial orientation or spatial disposition of the ligand surrounding the central metal ion. We have to see that these two ammonia ligands are side by side, and these two chloride are side by side. They are in the cis orientation. On the other hand, in this isomer, ammonia, they are in the trans orientation, and the chlorine is a trans orientation. So this is the trans isomer. Both are same, molecular formula is same. PTNH3 Cl2. The bonding connectivity is same with the ligand, but the spatial orientation of the ligand surrounding the metal ion is different. Here, because of the cis orientation, we call it as a cis isomer. And because here the similar type of ligands, they are anti-orientation, trans to each other. They are farthest apart. That is why you call it as a trans. That is why it is a trans isomer. Similarly, if I see Ma2BC type of complex, in this type A is any neutral ligand such as ammonia, pyridine, water, and B and C are anionic ligands like chloride, bromide, nitro, etc. So you see the example PTNH3 Cl NO2. Here what will happen? That we have to consider the same type of ligand, how they are orienting or how they are arranged with respect to the central metal ion. Here we see the cis isomer because the chloride and nitro, they are in the same site. The similar type of ligand, ammonia and ammonia, they are in the cis orientation. So that is why we call it as a cis isomer. But if the ammonia and ammonia, they are in the trans orientation or trans disposition with respect to the central Pt2+, then we call it as a trans isomer. So this is the case when the complex is Ma2BC type. There is an interesting case for MABCD type. MABCD type means where all the ligands are dissimilar. In this square plant complex, we can see that A, B, C, D are totally different ligands. So in that case, this complex can exist in 4 isomeric forms as shown below. We can see here A, B, C, D, then here A, B, C, D, A, B, then C and D, they interchange compared to 2 and 3. If you notice, here A, B are same, but here C and D, they interchange. Okay. And again, you see 1 and 4. AC are same, right? But D and B, here they are the C's. D and B, now they have interchanged. Here it is B, here it is D. So we can get the 4 isomeric forms of the complex MABCD. We can see the another type of square planar complex containing unsymmetrical bidentate chelating ligand MAB2, where AB is an unsymmetrical bidentate chelating ligands containing A and B are the two ends of the ligand. For example, PT glycinate 2, where glycine is NH2CH2CO-. This ligand is the bidentate ligand. Bidentate ligand means in the sense that it can coordinate through nitrogen lone pair or carboxylate ion. Now we have to see that when they are two ligands are there across the platinum, we have to see that how they are coordinated to the central metal ion. In this case, here the nitrogen is coordinating from this side, this ligand. Here also the same side nitrogen is coordinating. So NH2, NH2, they are in the cis orientation. Here carboxylate, O minus and O minus, they are in the same side. So from the same side they are coordinating. So that is why we call it as a cis isomer. But if it is reversed, reverse means in this case NH2, in this case oxygen, in this case O minus, and in this case NH2. So in this case we can call it as a trans isomer. So this is the scenario for square planar complex containing unsymmetrical. Why we call it as unsymmetrical? Because the two different coordination sites and also at the same time bidentate from the same ligand, two different coordination sites. So how they are oriented, the similar coordination sites, how they are arranged or oriented across the central metal ion. Depending upon that, we can decide whether it is a cis or trans. So in the case of square planar complexes containing symmetrical bidentate chelating ligand MAA2, we see here that here across the central platinum ion, this is a neutral ligand. So if we see the stereochemistry, all these methyl group, they are above the plane. If we consider the square planar complex, okay, this is as a plane. So these methyl groups, they are above the plane, and that is why we call it as a cis. Now if we see in this case trans isomer, here this methyl and this methyl, they are above the plane, while this methyl and this methyl, they are below the plane. So if we consider that square planar complex one plane, these two methyl groups, they are above the plane, and these two methyl groups, they are in the below the plane. Because of the trans orientation of these two methyl groups with respect to these two methyl groups, we call it as a trans isomer. So molecular formula is same, but due to the spatial disposition of the methyl group, one isomer we call it as a cis isomer, another we refer it as a trans isomer. So what will happen in case of bridged binuclear planar complex of M2A2B4 type? So in this type of complexes, cis and trans isomer as well as the unsymmetrical form also exists as shown below. If we consider that PT triethyl phosphate Cl2 whole 2, so this is a bridge ligand. Okay, so these two metal atoms are there, so this is a bridging ligand, this chloride and this chloride. Now if we see the position of the triethyl phosphate, like this one and this one, they are in the same site, so that is why cis form. Now if we see here, this is a trans position, right? So that is why it is called a trans form. Both are bridged, bridge complex. In this case, chlorine chlorine and triethyl phosphate. So this is the unsymmetrical form. So there are three isomers can be possible. One is cis form, one is trans form, another is unsymmetrical form. So far we discussed about the different square planar complexes and the isomerism exhibited by them. Now coming to the 6-coordinate complex. So what can be the geometry for 6-coordinate complex? 3 possible arrangements of 6 ligands around the central metal atom can be possible. Planar hexagonal, trigonal prismatic, and octahedral. The physical and chemical evidences, especially those based on isomerism, have shown that arrangement of 6 ligands in a 6-coordinate complex is always octahedral with all 6 positions are equivalent. So it has been shown the complex which exhibit the isomerism for the 6 coordinate complexes were octahedral. So now we are going to see what can be the different stereoisomerism for octahedral complex with the different types of ligands. In the octahedral complex, the arrangement of 6 ligands in a regular octahedral complex around the central metal ion can be represented as shown below. So this is the octahedral complex where the central metal atom or ion is there, and surrounding this 6 ligands are there. Okay, so we can call it as a 1, 2, 3, 4, 5, and this is 6. So this position of the ligands, we call it as equatorial position. 2, 3, 4, 5. If the 4 ligands are located at these 4 corners, we'll say that they are in the equatorial side. And if we keep this ligand here and here, that means 1 and 6 position, we call it as they are oriented axial. So axial ligand, okay, or apical site, okay. So these are equatorial site, these are axial site. So total 6 ligands. So now we'll see that what can be the different types of octahedral complex with the different monodentate bidentate ligand. So octahedral complexes containing monodentate ligands, it can be MA4B2 type, MA3B3 type, and MABCDEF type. Octahedral complex containing monodentate and symmetrical bidentate ligand, MA2A2 type, MA2AB type, MA2B2 type, where A is the bidentate ligand, symmetrical bidentate ligand. And another one, octahedral complex containing unsymmetrical bidentate chelating ligand, MAB3 type. We'll see the example of CONH34Cl2. So this oxidation state of cobalt is +3 and 4 amino ligand is there, which is neutral ligand, and 2 chloride. It will carry -1. So overall, this complex is +1. So 4 amine ligand and 2 chloride ligands are there. So if you see here, in this case, 3 amine ligand and 1 chloride ligand, they occupy the equatorial site. And 1 chloride is here and 1 ammonia is here. So if we see here, this chlorine and this chlorine, they are the cis orientation, they are side by side. Although this chlorine is in equatorial and this chlorine is in axial, but we call it as they are located side by side with respect to the central cobalt ion. So that is why we call it as a cis form or 1,2 isomer. Whereas in this case we can see they are transform. Transform means you see that this chlorine and this chlorine, they are trans orientation. Only in between cobalt ion is there. And all the equatorial positions are occupied by ammonia ligand. So these are axial site. So in this case, chloride, they are trans orientation. So that is why we call it as a trans form or 1,6 form. So this is the 1,2 isomer and this is the 1,6 isomer, right? So this is the typical example of cis-trans isomerism for octahedral complex. If we have the complex containing the symmetrical bidentate ligand like ethylene diamine, then what will happen? In this case, you will see that bidentate ligand, this position, this axial side and this equator are occupied by one ligand, bidentate ligand, ethylene diamine. This is also same, one equatorial side and this axial side. So these two positions are vacant. They are occupied by two chloride. So they are side by side. So that is why we call it as a cis form. In this case, the two ethylene diamine ligand are holding like this. They are coordinating like this. Okay. So the two axial sides are vacant. So this can be occupied by two chloride. So here they are trans orientation because the equatorial positions are occupied by two symmetrical bidentate ligand. So this chloride and this chloride, they are trans disposition. That is why we call it as a trans form. So this is cis form, this is trans form. So similarly, another example is chromium dioxalate diwater complex. So here two equatorial sides are occupied by oxide of the oxalate ligand, bidentate ligand, and here two positions are occupied by same oxide of another ligand. Okay. Now here one water molecule and one water molecule. This is equatorial side, this is axial side. So they are side by side, two water molecule. But here we will see both the equatorial sides are occupied by this bidentate oxalate ligand. So leaving behind this axial position vacant. So water molecule occupy here. So they coordinate through oxygen. So you see between the two water molecule, in between chromium is there. So they are in the trans orientation. So that is why we call it as a trans. So in this type of complex, we have to see the similar type of ligand, how they are spatially oriented. Whether they are in the cis orientation or trans orientation. Always you have to remember, if we say trans, in between the ligand, the metal atom or ion will be there. Okay. So in this complex also, this is cis and this is trans, because we have to pick up this ligand and we have to see what is their relative orientation with respect to the central metal atom or ion.